Thank you very much for the invitation. It's an honor to be in a row of Reinhard Genzel and Emanuel Bloch. Indeed, two very respective colleagues within the MPG. And I'll try to speak this direction because my microphone is on that side. And I will try not to get distracted by those. Anyway, thank you very much for having me here. It's 2014. It's nearly 100 years after Albert Einstein had presented his, is it possible to maybe dim that light, or maybe you don't see me then. Anyway, let's try. So it's 100 years after Einstein became a director at the Kaiser Wilhelm Institute of Physics in Berlin, and he was also then accepted to the Prussian Academy of Science. Perfect, thank you. Yep, excellent. And it was then a year later, on the 25th of November, 1915, when he presented his field equations for the first time. By the way, this is the Antrittsrede to the Prussian Academy of Science in July 1914. And what he presented nearly 100 years ago was what he called the theory of general relativity. And today, it's really one of the pillars of modern physics. It is describing gravity as the most fundamental long-range force. Therefore, it lies at the heart of understanding of the cosmos, how it evolves, and what the future of the universe is about. And it's also one of the best tested theories ever. And, but still, the question is the theory of general relativity our final word in understanding gravity? Well, as I said, it's one of the best tested theories that we have. And there's some classical tests. Einstein was very happy, for instance, that he was for the first time able to explain the perihelion advance of Mercury. Mercury isn't on an ellipse, but actually the ellipse is rotating in space. And astronomers didn't understand why that is happening. But Einstein, with his theory, was for the first time able to explain this. Of course, most famously is perhaps the prediction that light is deflected by mass, and that was an experiment that was done immediately after the First World War in 1919 at the first solar eclipse. So the idea is very simple. You see that this light of a star is bended in its direction by the gravitational field of the sun, basically by the curvature of the space-time around it. And for an observer on Earth who doesn't know that the light is bended, the apparent position of the star is shifted relative to the original, the true position of the star. Now, in order to do this experiment, you have to observe a star very close to the sun. And that is usually not possible because the sun is too bright. But every now and then, we have a total solar eclipse where the moon, which has just the perfect size to black out the light of the sun, then the stars around the sun become visible, and then you can do this experiment. And so indeed, the Royal Society organized an expedition that sent two teams. This is the path of the solar eclipse in 1919. This is the shadow of the moon. Here is actually seen from the moon. And there was a totality region in South America and Brazil, and another one in West Africa. And the Royal Society sent two teams, one to Brazil, one to Western Africa, to take an image of the sun. And this is the image that is presented by Eddington later. And you can't really see this, maybe here better now. This is two green points here which show the shift of the position in the star during the measurement of the eclipse and to measurement at some other part of the year. And the shift agreed with the prediction of general relativity, and Eddington sent a telegram to Einstein to congratulate him that the theory was actually working. And Einstein, this is a letter, you may not be able to read this, this is a letter that Einstein wrote to his mother, where he says, Liebe Mutter, heute habe ich eine freudige Nachricht erhalten, and so on and so on. He actually tells his mother how proud it is that his theory actually works. So that was a triumph for general relativity, which really made the world headlines. We also, of course, have later on, it was the gravitational redshift was measured. I'll say more about that later on. But today we have modern experiments, mostly in the solar system. For instance, we have so-called lunar laser ranging. This is the best evidence that the Apollo astronauts were actually on the moon because they left laser reflectors on the moon's surface. And nowadays we shoot lasers from the Earth's surface to the moon's surface. And when it bounces back from these laser reflectors, we can measure from the light travel time the distance between Earth and moon very, very precise, to better than a centimeter these days. And by doing this, you can see how the Earth and the moon fall in the gravitational potential of the sun, and that allows you to test the theory of gravity. We can also do this on longer ranges in the solar system by sending radar signals to planets, or we take the signals of spacecrafts like the Cassini probe and do this very similar experiment. Or we have satellites orbiting the Earth, like the LEGOs or the Gravity Probe B satellites, which try to measure the gravitational field of the Earth and the impact that it has on the orbiting satellites. All these tests have been passed by General Relativity. We couldn't find a single flaw. And so you can ask the question, like we did in 2006 in the Einstein year or the year of physics, was Einstein right? And for reasons that I explain you later, I happen to visit Australia quite frequently. So when I picked up the Australian issue of Sky and Telescope, I got that question. It's probably the upside down, I don't know. But the question is really much alive because we have some problems. Precision cosmology, which wasn't possible or even thought about it at Einstein's year, says we had a period of inflation in the universe, a period where the universe expanded very, very rapidly. We have no physical model how that works. We just don't know how it works. It's just that the data are consistent with inflation, but there's no physical model. We don't know what dark matter is. We know nowadays that dark matter, some mysterious matter that interacts with gravity, makes about 20% or so of what we have in the universe. We don't know what it is. All dark matter experiments have so far failed to identify whatever that material is. And even more curious, there's something what we call dark energy, which makes even about 70% of the universe. It seems to push the universe apart, in particular right now. We have no real idea what it is. That's when the astronomers don't know what it is, they call it dark something. So it could be a new force, it could be new physics, but it could also mean that we haven't understood gravity. And so therefore, this question whether Einstein is right or wrong is very much alive. Also, we know that general relativity, as a theory that explains the universe on very large scales, is completely incompatible with the theory of quantum mechanics, which explains the world very well on very small scales. How do they interact with each other? So, in fact, most of us believe that general relativity will fail at some point. But what do I mean by some point? Is it very much below the Planck energy, or is it something we will not ever be able to measure? And so that really bothers us right now. Where does general relativity fail? So what we try to do in our experiments, and that's what I'm going to explain you in the following, is we're trying to push the limits. We're trying to go through the most extreme objects and systems that we find to see if general relativity holds. So if you think about what we have tested so far, there is what we call the quasi-stationary weak field regime, which is apparently flat space-time, which we can test very nicely in the solar system in the way I just explained. When you start, however, to look at the gravity theory, you really want to understand how gravitational waves work. That's the prediction of general relativity, but also alternative theories of gravity. I'll come back to that. And the question is, how do they propagate? And at the moment, the only single way of exploring that is with so-called pulsars, the topic of my talk. And so I'll spend a lot of that on my talk. However, really what we need to test is what we call the radiative regime, or the so-called highly relativistic regime. That's where we want to detect gravitational waves directly for the first time to measure their properties. And again, I will explain you how pulsars will play a role, and also, of course, the so-called gravitational wave detectors, like the one in the US and in Europe in near Pisa will play an essential role to detect gravitational waves in the next few years, and then we can actually look at the properties. So when we want to test gravity, we need to do it where gravity is strong and nonlinear, because that really tests the extreme. And we must test the radiative properties of gravity. Any theory that has not predicted what the radiative properties of gravity are cannot be used. Right, so as a very short introduction, a longer introduction is I explain you the kind of experiment we do. I explain you the technique. I then explain you, tell you a little bit about the first binary pulsar that won the Nobel Prize in 1993. I'll then tell you what our best gold standard is these days, the so-called double pulsar. I'll then talk about on a very few slides on some of which is my favorite topic, relativistic spin precession. And then I'll say a little bit about alternative theories of gravity, because general relativity is not the only theory that we deal with. It's the best tested and the only successful so far. But as I said, there are reasons to believe that there could be deviations or alternative variations to general relativity. And finally, at the very end, if I have time, I'll say a little bit about the future experiments in the near and far future. Okay, let's show you what we do. Okay, what we use is a clock. It's a cosmic clock that we use that we call pulsars. A pulsar is a so-called neutron star. It's an object that forms at the end of the lifetime of a massive star. When the star collapses, it condenses matter on such a small radius, 20-kilometer diameter, that it's very compact and mostly consists of neutrons. And it consists about 1.4 times the mass of the sun within 20 kilometers. That's the most dense matter that we can observe in the universe. It exceeds the nuclear density by about an order of magnitude. It's the only matter that we can observe that has these properties. We will never be able to reproduce it here on Earth. When the pulsar rotates, it emits a radio beam that is inclined to the rotation axis, and it's like a lighthouse. Whenever the beam points in your direction, you see a pulse, like now, 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 and so on. So every pulse that we receive corresponds to one rotation of the neutron star. And the rotations span 4 orders of magnitude. The slowest rotating pulsar has a period of 8.5 seconds. So I can gently turn around in almost 10 seconds, and that's the slowest radio pulsar that we know. If I tried to do the same simulation for the fastest one, I had to do this in 1.4 milliseconds. I won't even try. In between, we have the famous Wheeler pulsar, which is the strongest pulsar in the sky, with an 89 millisecond, and the Krebs pulsar, which is maybe the most famous one, which is in a supernova remnant that we call the Krebs nebula, which has a period of 33 milliseconds. Now they're tiny, and I would like to show you a picture, but I can't. But I can make them hear you. This is the Wheeler pulsar. Every pulse, 89 milliseconds. You can actually see here the variation in the pulses. They're not all the same. So there's variation in amplitude, but the period is very exact. The Krebs pulsar are 3 times faster. So every 33 milliseconds, you receive a pulse. The so-called millisecond pulsars, the fastest rotating pulsar that rotate with millisecond periods, here the tone is too fast, the pulsar too fast to be separated by your brain. What you hear is something like this. This is a tone of about 700 hertz. And remember, this is the rotation of an object of the size of the city with a mass of 1.4 times the mass of the sun. So in rotations per minute, it's in red, sorry, this is about gentle 7 rotations per minute. If you go home and wash your laundry and look in the tumble, in the whatever that is, it's about 1,600 rotations per minute on high speed. You think that's a lot? Well, if you could afford an engine like a car like this, that does about 20,000 rotations per minute. But it's really nothing compared to what the city-sized object does oops, can't see this, 43,000 rotations per minute. And this thing doesn't fly apart. The centrifugal forces are enormous, but it still sticks together, and that's one of the proofs that we have to do with some very compact, very gravitational object. And that's what we call a pulsar in a Newton star. When we observe it, we take a telescope like the 100-meter telescope of our institute. We observe the pulsars, and what we see is indeed regular pulsars. As you can see again, the amplitude is different, the pulse shape is slightly different, but they come with the regularity of a clock. And so what we do, we time tag the arrival times with our local atomic clock, and we synchronize that with GPS to an international time standard. And what we have is we measure the arrival times of the pulsars at our telescope and compare them with the best atomic clocks that we have on Earth. And then we do a simple experiment. So usually the pulsars are not as strong as you've seen here. This is the strongest pulsar in the northern sky. But the pulsars are usually weaker than the noise because our measurement telescopes are big, but not big enough to see single pulsars. Not yet, anyway. So what we do, we fold, as we call it. We sum up the pulses with the right pulse period to increase the signal to noise. And once we have sufficient signal to noise, we measure the so-called time of arrival, a TOA. Then we have a certain model. We know how the pulsar rotates, and we predict the next arrival times into the future. So we have a model that for every rotation predicts the arrival time. Then we repeat the experiment and compare the newly measured arrival time with the model. Typically, we see a deviation, and we call that a residual. But by repeating this experiment and again, we make the model better and better so that we essentially have only random distribution around 0 with our residuals. And at the end, what we have done, as you can see, we can actually count every single rotation between one measurement and the other. And that's what we do. We count rotations. We're not measuring pulse periods like you do maybe in other parts of astronomy. We actually do a ranging experiment. And that ranging experiment is about 1,000,000 times more precise than if you would just take simple Doppler measurements. And that is the key to our experiments. What we do in the following is pure physics, based on astronomical measurements. So, for instance, a pulsar that we time, actually it's almost like 20 years by now, I should really update that slide. This is a pulsar which has a 5.2 or 5.3 millisecond period, and we know this to a precision of 0.00000000015 seconds. And that's even not the most precise period that we have. In other words, this error means that the pulsar has done 100 billion rotations since we discovered it, and we haven't lost a single count. I can go back to the telescope in 30 years and make a measurement, and I can tell you exact to the rotation how many rotations the pulsar has done. That's the precision we have. And so the experiment is quite simple, at least from the concept. We look ideally at a pulsar which orbits a companion, which falls in the gravitational potential of the companion. And both of them fall in the gravitational potential of the Milky Way. And astronomers, we just sit there and look. This is our laboratory, and we just sit from the outside and look. And we can do this we know about 2,200 pulsars, of which about 10% have this binary companion. And at the moment, we know main sequence star companions, about a handful. We have lots of white dwarf companions. More or less 90% of those have white dwarf companions. And then we have a couple of Newton stars as companions. We also found the first extrasolar planets. They were found around pulsars, not around ordinary stars. And we have one double pulsar that I'll talk about more in the following. What we haven't found yet is a black hole as a companion. And that is the goal, the remaining holy grail that we try to find. But anyway, using this kind of laboratories, our experiment is rather simple. We just sit there and see how this object falls in the gravitational potential of the Milky Way and how they fall around each other, and we compare our observations with the theory. And we can do this with very high precision. And this is a kind of a show-off slide. The number in digits, in brackets at the end, is the error or the uncertainty in the digit before. So for instance, the most precisely measured period is this one here of a 5.8 millisecond pulsar, which we have measured to a precision of 2 attoseconds. That's a 2 with 18 preceding zeros. We can measure distances and periods, orbital periods. We can measure masses very precise. For instance, this is quite nice. We can measure the mass of Jupiter and its moons to a precision of 9.4, 10 × 10⁻⁴ solar mass with that precision. That accuracy is identical to that achieved by flybys by Voyager and Pioneer. And we can do this just by observing pulsars, because Jupiter determines where the center of mass is in the solar system. And if we don't know that well enough, then our data don't make sense. And so we can actually convert this into mass measurement of Jupiter. I'll tell you more about relativistic tests, but maybe one number that I want to talk about on 2 slides is this one here. As I said in the beginning, we also try to detect gravitational waves using pulsars. And the way we do this is by looking at lots of pulsars in different directions, and we try to see what happens if the gravitational wave passes the solar system and changes the distance between us and the pulsar ever so slightly. And we have already achieved a precision that corresponds to measuring a distance change of 100 meters over 1 light year. That's already achieved. What we need to do to detect gravitational waves is about a factor of 3 better. We need about 30 meters per light year. And so this is the kind of experiment that we want to do. We call it a so-called pulsar timing array. We're sitting here on Earth. We're observing all these different millisecond pulsars, an array of pulsars. And as a gravitational wave propagates over the Earth, it pushes Earth a little bit. And so it affects the arrival time of the pulses on Earth that we measure in a correlated fashion on the sky, which is plotted here. That's a so-called Hellings and down curve. This is the correlation coefficient as an angle between the pulsars. I won't go into detail why the curve looks like this. You can ask me later. But if you see this correlation on the sky, you have detected gravitational waves for the first time directly. And of course, everyone tries to do this right now. The signal that we're trying to find, is one that comes from the early universe. The astronomers believe that all the galaxies, including our Milky Way that we see around, was formed from of smaller galaxies forming a bigger one, like in this animation here. And in this process, once the 2 galaxies collide, there's a period when the supermassive black holes in the center of these 2 galaxies have a cosmic dance and form a binary system of supermassive black holes. And they typically have orbital periods of the orders of years, and that's exactly the frequency range for gravitational waves that we are sensitive to with pulsars. And again, I won't go into detail. This is just a preview. Hopefully, we can tell you much more in a few years' time. But this is the frequency, the parameter space, the spectrum of gravitational waves. This is the characteristic amplitude by how much the space-time is changing a length on Earth. This is the observed frequency. You know about the LIGO. I mentioned this already. They sit here about kilohertz. There will be hopefully once a space interferometer for gravitational waves, which works in kind of micro and millihertz. And we are sitting here with pulsars. We are sensitive to nanohertz. And actually, this is the expected background from this kind of signal. And you can see we are actually already very, very close. In fact, we have reached the level where the signal should be. With the SGRAL, I'll say a few words later on, this will be trivial. This will be a high precision measurement. But for now, we are really at the edge of detecting something. So stay tuned, and maybe there will be a talk at some other point. So why do we spend all this money on gravitational wave detectors? After all, it's a prediction of general relativity. But as I said, there's only one evidence that they really exist, and that comes from pulsars. And that brings me to the first binary pulsar ever discovered, the so-called Hulse-Taylor pulsar, because it was discovered by Russell Hulse and Joe Taylor in 1974. They did a survey with this Arecibo telescope that you may know from GoldenEye, where it's sort of filled with water. It was only a trick, believe me. and maybe also contact. And they observed the sky. They did a survey for unknown pulsars, and they found in 1974 an object that was changing in the pulse period from 59.06 milliseconds to 58.97 milliseconds. And after they got this curve, it's quite clear that this is the binary pulsar with a highly eccentric orbit. What the difference comes here from Doppler variation of the orbital motion. And nowadays we know it's a binary pulsar with an 8-hour orbit in a rather eccentric orbit. And so that's what they found. It was not only the first binary pulsar to be discovered. As I said, we have about 200, and only 10 of them have another Newton star companion like here. The most common one is a white dwarf as a companion, and yet at the very first try, they found this amazing system. Why it's so amazing? Because we have two compact masses, two Newton stars, orbiting each other in 8 hours. And then general relativity predicts a lot of different effects that are inconsistent with the Newtonian description of the orbit. So if you believe in Newtonian physics, you would be able to describe the orbit of the system that they found, and they found one pulsar and an unseen companion. That becomes important on the next two slides. So they found one pulsar that was orbiting an unseen companion, and if you believe in Newtonian physics, you can describe the orbit by just 5 parameters. The binary period, so how long does it take for the pulsar that rotates around its companion, the size of the orbit, the eccentricity of the orbit, so the so-called longitude of periastron, that's sort of a measurement, where do they get closest to each other, because the distance changes, because the orbit is eccentric, and the so-called epoch of periastron where this happens. However, within a couple of days, they realized this doesn't work. They need to modify the description of the orbit. They have to put add-ons. Nowadays, we do differently what they've done 40 years ago, but what we do nowadays is we describe the orbit additionally by so-called post-Keplerian parameters. That's an expression I'm going to use in the following. These are theory-independent corrections. Theory-independent is the underlined thing to describe the arrival times that we measure on Earth. So for instance, they found that the orbit is precessing in space, just like in Mercury. And you describe this by just the time derivative of the Newtonian value. They also found gravitational redshift. I explain that in a second. They found that the orbit is decreasing. That was the exciting bit, and I'll tell you more about that as well. And then they didn't find, but we find this another pulsar these days, so-called Shapiro delay, and I come back to that. So the idea is very simple. If we see deviations from Newtonian physics measured by these post-Keplerian parameters, all we do, we measure these post-Keplerian parameters by observation and compare it to the theory. And the theory of your choice should make a prediction what the values of these numbers are. And so you can just compare these numbers. And so that's exactly what they did. So the first thing that they noticed, was the precession of the orbit. So again, the ellipse of the pulsar is apparently precessing in space, rotating in space. And the observed rate of precession was about 4.2 degrees per year. Now, you can write down an equation for that in general relativity. As I said, every theory of gravity should predict these numbers. And in general relativity, that is the equation. This is the gravitational constant, the speed of light, the orbital period, the eccentricity of the orbit, and the two unknown masses of the system. Now, I'll show you only a few equations in this talk. If you have questions, ask me. Otherwise, ignore the equation if it's too much trouble. But this is a simple one. They also found gravitational redshift. So what does that mean? General relativity predicts that the clock in a gravitational field goes slower than outside the gravitational field. For instance, if you have a skyscraper on a Newton star, not highly recommended, but if you had, the clock on the lower floor would go much slower than the clock on the upper floor. And in fact, it has been tested on Earth by flying two atomic clocks in the plane and one on Earth. And if you compare them and calculate other effects, you indeed find that the clock that was on the Earth's surface goes a little bit slower than the one that was on the plane. Here in a pulsar, it's very simple. We have a pulsar clock that orbits around its companion, the center of mass, and at some point of the orbit, they're closer to each other, and so it feels the gravitational potential deeper, and the pulsar clock goes slower. And at some other part of the orbit, they're further apart, and then the pulsar clock goes a bit faster. And what you get is a variation in the clock rate. And the amplitude of that was about 4.3 milliseconds. And again, you can write down an equation, and it looks slightly different, but it has some same features. It has some constants, the Keplerian parameters like the orbital period, the eccentricity, and the combination of the two unknown masses. Anyway, so we have two equations and two unknowns because everything else is measured. We can solve for these two masses, and you immediately get a measurement for the two neutron stars' masses if you believe in GR, if you believe in general relativity. Now, the important point is, and I tried to imply that by writing down the equations explicitly, you can actually show that all post-Keplerian parameters can be written as the functions of only the observed Keplerian parameters, which you measure to high precision, as I've shown, and the two unknown masses of the pulsar and its companion. So if you have two post-Keplerian parameters, you can calculate some masses for a given theory of gravity. And then the theory of gravity, then you take these two masses and stick them in the theory and make the predictions for the other parameters. So if you measure a third, fourth, or fifth parameter, you can actually make a test. And indeed, for the Hulse-Taylor pulsar, the other test is the detection that the orbit is shrinking. And this is maybe the most famous plot, at least in radioastronomy, I think, arguably anyway. What does it show? It shows the existence of gravitational waves in an interesting way. As the pulsars or the pulsar orbits its companion, general relativity predicts that it creates waves in space-time, ripples in space-time that propagate away from the system. And as the wave propagates away from the system, just like here, it removes energy from the system. And if you remove energy from a binary system, it shrinks. And when it shrinks, the pulsar reaches its periastron, so the time of closest approach, earlier and earlier and earlier because the orbital period is decreasing. And that's plotted here. This is the change, the cumulative shift in periastron time as a function of year. And this line here, you may notice, is not a fit to the data. It's the prediction by general relativity based on the two masses that I've shown you before. And it fits beautifully. It confirms the measurement points. And that's the reason why Hulse-Taylor received the Nobel Prize for discovering the system, because this is the first evidence for gravitational waves. Again, you may think, okay, that's all nice and we have done. But actually, you have to be a little bit closer in this example here. For instance, if you actually compare the observed value of the shrinkage of the decay of the orbital period, you find that the observed value is actually not agreeing with the value of general relativity. You have to apply a correction to make them agree. And the correction comes from a relative motion of the pulsar and the relative acceleration from us and the pulsar system. And I won't go into detail, but unless you know how far the pulsar is away and how far it's moving, and whether it has a relative acceleration between us and the system, your observed value will differ from the expected value in general relativity. And so we have to make a correction. This was measured by Taylor and its collaborators, but it's only measured to 0.2% precision, and that's as best we can do. The pulsar system is now for 40 years, but this number hasn't improved. The uncertainty in the test hasn't improved now for about 25 years, because we are unable to make that correction better known. With Gaia, the astrometric satellite that has been recently launched, this will hopefully change, but for now, we're stuck with that test. So this is a test that confirms the quadrupolar nature of gravitational waves. I'll say more about what that means. But this one, it has been hadn't improved for 25 years. until we found another system. Okay, let me explain that first. So there's an elegant way, actually, to make that test that I just showed you by solving equation in a graphical form. That was first introduced by Damour and Taylor in '92. As I said, you can always show that the post-Keplerian parameters are just function of the Keplerian parameters, measured very precisely, and the two unknown masses. And again, I have the number here for the precession of the orbit, the equation. So you can invert this equation in a form that you write down a function for the mass of the companion that is a function of the mass of the other pulsar parameterized by the Keplerian, post-Keplerian parameters. So, oops, spelling mistake. And so what I do is I try to invert this function and write down an equation for mc as a function of mp. And then I can plot this one mass and the other mass in a so-called mass-mass diagram. So for every post-Keplerian parameters, I can produce this function, and I can draw a line in this diagram. Again, mass of the pulsar versus mass of the companion. So if I have two measured values, like before the periastron, the longitude of periastron, and for instance, the gravitational redshift, then you will have an intersection point which gives you the masses of the system for this theory of gravity. For every theory of gravity, the lines will be different. So what we now measure is a third parameter, and that gives you a third function. So the third function, however, could miss the intersection point. And if you see something like this, your theory of gravity is inconsistent, and the theory has failed. What you would like to see is that all lines intersect in a single point, defining one single value for the masses of the pulsar and the masses of the companion. And so what I will show you in the following is a couple of these diagrams for various systems. However, if you look for that for the Hulse-Taylor pulsar, this is the longitude of periastron, this is the gravitational redshift, and this is the orbital period decay. They all seem to intersect in a single point. However, if you don't do the correction and you zoom in, you'll see actually that they fail. But it's not a failure of general relativity, but because of this external effect that you have to take into account for. So this was kind of unsatisfactory. So fortunately, in 2004, by now, we discovered we discovered what we call the double pulsar, which is much better than the Hulse-Taylor pulsar in many, many respects. What we found is the first system where we have two active radio pulsars orbiting each other. And that's for the first time ever happened. So we have a 22 millisecond pulsar and a young 2.77 per second pulsar and 147-minute orbit. They have orbital velocities of about 1 million kilometers per hour. The eccentricity is small but not zero, and so they also change the distance in the orbit. And it's an ideal laboratory for fundamental physics, in particular for theories of gravity. So what we have here is really the first binary pulsar with two active pulsars. One is fast here in the background, one is slow here in the foreground. And in fact, we see the orbit edge on, so that every 30 seconds, every orbit, we get a 30-second long eclipse where the foreground pulsar eclipses the background pulsar in its light. And that is actually allows an interesting experiment I will also show you in the following. Here is a radio observation of the two pulsars. These are the pulsars of the slow pulsar, what we call B in the following. And we have taken out the Doppler shift, so that's why it's going up here. And in the background, you may be able to see this. There are some parabolic arcs, which is the fast pulsar in the background shining your telescope at the very same time, only much faster. So why is this system so exciting? First of all, in comparison to the Hulse-Taylor pulsar, it's much closer to Earth. This is the Earth, this is the relative position of the double pulsar, and this is the Hulse-Taylor pulsar. The Hulse-Taylor pulsar is about 8 kiloparsecs away towards the center of the galaxy, where we don't know the gravitational potential very well, and that's the reason why we can make this correction better. But the double pulsar, it's less than a kiloparsec away from Earth, so it has no relative acceleration that we can talk of, and it's much more compact as well. It fits into the sun, so it has much more relativistic effects that we see in the Hulse-Taylor pulsar. But first of all, we see two orbits. We have two clocks, not only one clock, falling around the same center of mass. And so the two sizes of the orbit give you immediately the inverse ratio of the masses, which makes sense. The heavier pulsar is closer to the center of mass than the lighter pulsar. And this relationship is theory independent, at least what is called the first post-Newtonian order. And we can measure it. So we have a mass ratio. We can also measure the period, the orbital period to very high precision. For instance, the period of pulsar A, we measure to 0.2 picosecond these days, and the orbital period to about 700 nanoseconds precision. We also see the periastron advance, the same effect as Mercury again, only much faster. For Mercury, it takes about 3 million years for this additional rotation of the orbit. In the double pulsar, the same happens on a timescale of 20 years. So you can actually do some few PhD theses around this. So here we have a value of almost 17 degrees per year, which is a factor of 4 larger than what we found with the Hulse-Taylor pulsar. We also have the same clock variation. This time it's much less in size than the Hulse-Taylor pulsar, but we can also measure it very precisely. I don't have to explain this effect again. We also see the curvature of space-time. This is the Shapiro delay that I was alluding to earlier. The mass determines the curvature of space-time around it. So around the compact sister object like the Newton star, space-time is not flat, but sort of has a dip. And so if the pulsar, if one light of the pulsar wants to pass the companion, for instance, superior conjunction, then it has to go to this tip of space-time, which takes slightly longer than going through flat space-time. And that leads to a delay of our signal by about 100 microseconds. By the way, this is what we published in 2006. That is what we're working on right now. You can see how much better the data quality is. So that is that's actually the direct evidence for the curvature of space-time. And we can use this actually to also measure the inclination angle of the system, which is indeed close to 90 degrees, which means we see the orbit from edge on, as confirmed by the eclipses. And it allows you also to measure the mass of the companion independently. And of course, we measure that gravitational waves exist. For instance, the pulsar period, the orbital period decreases every day by 107.79 plus minus 0.11 nanoseconds. In other words, the two Newton stars, the two pulsars, approach each other by 7.152 plus minus 0.008 millimeters, which means in 85 million years, they produce a gamma ray burst, the two Newton stars collide and probably form a black hole. But we can now look at how good that value is in comparison to general relativity. And you'll find that we have an agreement now which is almost an order of magnitude, well, exactly an order of magnitude better than we had with the Hulse-Taylor pulsar. So if I show you this diagram again, this is the Hulse-Taylor pulsar. This is the change in periastron time as a function of year. This is what we predict from general relativity for the double pulsar. And these are our measurement points. So this is by far the best confirmation that gravitational waves exist, and therefore it's worth spending all this money on detecting them directly. Now I introduce this diagram. This is what it looks like right now for the double pulsar. You have different lines. They all intersect in this single point, which you can't see, so I've blown it up here. And even here you see the error uncertainty that we have in our measurement, at least in some of them. And that's where they intersect. You can even not see that anymore. So each of these lines, as I said, corresponds to a different relativistic effect. And each of these, after more than two lines, has the potential to fail this intersection point, but none of them does. And so we have the mass ratio, I explained this already, which is theory independent, so the intersection point has to lie on this line, which it does, plus 6 post-Keplerian parameters, so we have 7. We need 2 to identify the intersection point, which leaves you to 5 independent tests of GR. And as you can see, all of them passed. This is more than any other system. So these are all 5 really independent tests in just one system. Now actually, if you count carefully, if you ignore the Shapiro delay, there's 1, 2, 3, 4, 5 post-Keplerian parameters. And here I've written 6. So I haven't told you about the 6th one yet. So I'm going to come back to that now. Right. So if I would have been not, well, there's another effect that is called geodetic precession that is predicted by general relativity. If you want to do some homework, go home, take an empty piece of paper, draw a circle, and then draw parallel lines at the edge of the circle. Then take a pair of scissors, cut the circle, and then also cut from one edge of the circle to the center. So you have a circle with a cut from the edge to the center. Then you take that and you fold a cone. And then you look into the cone, and you will see actually that the ticks that you made at the edge of the circle, which were parallel, are not parallel anymore. After one circle around, they actually have an angle to each other. And so what you found is essentially a property of geodetic precession. It's just the nature of curved spacetime. And so if you have a gyroscope or spinning thing that orbits around the curved spacetime, after one orbit, it points in a different direction than in the start. Do this experiment, you will be amazed. And so a pulsar is nothing else than a gyroscope. You draw, it orbits the center of mass, and it will point in a different direction at the end. We call that geodetic precession. It was first predicted by Damour and Ruffini immediately after the Hulse-Taylor was found. And in fact, we found it for the Hulse-Taylor pulsar. But for the double pulsar, it has an interesting side effect. It changes the eclipse that we have for each orbit. So for instance, this is the eclipse that we observed in 2003. This is for the background pulsar A. The pulsar A is on here. Then it becomes dark, and it becomes bright again. And this takes about 30 seconds. In November 2007, it looks a bit like this. And what you can see are these spikes. There's some spikes here which are missing here. And when we looked first at the data, we thought it's just random noise. But it's not. It took a young, bright postdoc to tell us, actually, that these spikes are not random, but they're actually spaced at the beginning by half the rotating period of pulsar B, and then later that changed to full period of B. And she was absolutely right. And we can easily understand this. So this is the magnetosphere of the foreground pulsar. This is the spin axis, and this is pulsar A in the background. And now we run into the eclipse. So we start to observe. I think it's already as loud as you.
Is the pulsar or is the?
It's fine. Sorry, it's the signal. Thanks for your help. Let's start again. This is actually the noise of pulsar A in the background, 22 milliseconds. And now we run into the eclipse. The pulsar is now blocked, visible, blocked, visible, blocked, visible, blocked, visible. So every half a period, you see actually the light coming through. Blocked, visible, blocked, visible. And at the end, at some point, we run into a phase where it switches the period. Blocked, visible, blocked, blocked, visible, blocked, blocked, visible. That's where we change from half the period of B to the full period of B. And it's very sensitive to the orientation of the spin axis. And at the end, I will overlay some red colors, and you will see that the data are perfectly fitted by a model that contains only 4 unknowns, which is just the geometry and the size of this donut. We can explain every single spike. And you can do this as a function of time. And then you will see that the eclipse pattern, this is the time here, and you see the spin axis rotating, is actually changing as a function of time. And by doing fit over all these years of data, we were able to measure the precession rate of this, and this agrees with the prediction of general relativity to within 13%. It's the first time that we can do this test quantitatively, not only qualitatively as we've seen it before, but for the first time quantitatively. Right. So again, is that it? Is that the final word? Let's have a quick look at the alternative theories of gravity and what we can do in constraining them. And one theory that is very popular is so-called MOND, modified Newtonian dynamics, and it was invented to avoid dark matter and to actually, because there are some, if you look at the rotational speed in galaxies as a distance from the center of a galaxy, the curve doesn't go down as you would expect it if you just based your measurement on the visible light, but actually it's a flat rotation curve. And we think that there is a dark matter halo, which explains why this doesn't go down. But other people think it's a misfunction of gravity, and so they modified it. And this is Milgram's initial approach. He basically thinks that you have sort of Newtonian acceleration if the acceleration is large, but if the acceleration becomes small, you shift to a different law. And he chose that number here where this crossover happens such that it's not measurable in a solar system. Clever. Anyway, to make this a viable theory, Bekenstein converted this into relativistic theory of gravity. I won't go into detail, but if you look at this Tevis theory, as we call it now, because in addition to the tensor that we have in general relativity, we also have a vector on the scalar field. This is the mass-mass diagram for Tevis. And as you can see, it's far from being one single intersection point, so this one is certainly ruled out. Scalar fields, however, are very popular right now because they are a standard explanation for dark energy. We find them in unified, in superstring theory, we find them in inflation theories and quintessence and other dark energy models, but also dark matter models, as I said, involve scalar fields. And again, I won't go into details, but we have a scalar field in addition to the tensor. And in the most studied class of tensor scalar theories, you have just two additional parameters, what we call alpha naught and beta naught. And in relativity, they are zero. In scalar theories, tensor scalar theories, they may have a non-zero value. And what we try to do is try to have an experiment that let us constrain these values alpha naught and beta naught, and let's have a look how close they are to zero or they are not. You can do this in a solar system again, and then you plot your experiments on a diagram like this. You have alpha naught on this axis, beta naught on this axis, and everything below a line is given by an experiment, for instance here lunar laser ranging or Cassini, I mentioned this already. Everything below a line is allowed. Everything above a line is forbidden. And general relativity lies here at the origin where both values are zero. So let's see what we can do with binary pulsars to do this. And here we use the fact that most alternative theories, including tensor scalar theories, violate a fundamental principle of general relativity. That's the strong equivalence principle. What does it mean? It means that all bodies, regardless of the gravitational and chemical composition, fall the same way in a gravitational field. It doesn't matter whether you take a Newton star or feather, they'll fall the same way in a gravitational field. But most theories of gravity that are alternatives violate this at some point. And if you do this, then it matters what this object looks like. So if I have, for instance, Earth and the Moon, and they fall in the gravitational potential of the Sun, then the Earth and the Moon fall differently. And that's what's measured by lunar laser ranging. But you can also take a pulsar and a companion. If they fall in the gravitational potential of the galaxy, they will also fall differently, and that leads to effects, in particular to the emission of gravitational dipole radiation. So you have a mass dipole. So rather than just, in general relativity, graviton is a so-called spin 2 particle, and the strong equivalence principle holds, and you only have quadrupole emission. But if you have a scalar field, a so-called spin-zero particle, you actually get maybe a monopole, maybe, but certainly a dipolar term. And that dipolar term is usually much larger than a quadrupole term. So all we do, look for dipolar radiation. Do we see it? Here, the double pulsar is actually not very good because this scales what we call sort of the scalar charge of your body. And the double pulsar, we have two Newton stars. They're very similar. So these two numbers are very similar and hence close to zero. What you really like to find is a system where this difference is large. And the best object to find would be a pulsar around a black hole, because a black hole doesn't have a scalar charge, and that number would be maximized. As I said at the beginning, we haven't found a pulsar black hole system, although we try. And so the best next thing is a pulsar white dwarf system. Again, two different objects. And we did that experiment very recently. We looked at the pulsar which has a bright white dwarf companion that we observe with the VLT. It's visible in the optical, and we can measure a Doppler variation of the white dwarf in its orbit. That gives us the radial velocity, together with the radial velocities from the pulsar that we measure with Effelsberg and other telescopes. We can again measure the mass ratio. But we can also do spectroscopy on the white dwarf because it has a nice hydrogen atmosphere. We can do high precision modeling, and we determine the mass of the white dwarf. We know the ratio, we know the mass. You get the mass of the pulsar, and to our surprise, it is heavy. It's much heavier than you would expect from the Chandrasekhar mass. In fact, it's the most massive Newton star we know. It's above 2 solar mass, and that error bar by now has become much smaller, by the way. So this is nice because it also helps us to constrain equation of state, which means the Newton star has to sustain a really large mass, and that tells us about superdense matter, but that's another talk. So let's see what it means for this diagram. So I'll concentrate now. We are here with pulsars. We are much better than anything in the solar system. So let's see where we are. This is now a logarithmic scale. This is beta naught. This is alpha naught. This is the origin with GR. And this is our constraint, which is now, for almost everything in the parameter space, much better than anything in the solar system by Cassini. We have other pulsars now. This is one of the one we published before. Oops, no, I don't want this. Sorry. This is a stupid sound. And in the future, what we really like to have is a pulsar black hole system. And as you can see, it would be the best system ever to constrain this alternative theory of gravity. But in any case, even now, there's hardly any parameter space left for the scalar charge to be there. OK, a quick word what we do want to do in the future. I already pointed out pulsar black hole system would be nice, but they're very rare. So for the last 2 minutes, let me explain you how we find them. The best way to find a pulsar with a black hole companion is to find all the pulsars in the galaxy. And we can do this. There are about 30,000 normal pulsars to be observed. There are 120,000 in the galaxy, but we only see those that point towards Earth. About 2,000 millisecond pulsars, 100 relativistic binaries, so 100 times these experiments that I just described. And there will be some with a black hole companion. And what we do to find all the pulsars in the galaxy is a telescope that we call the square kilometer array. You can ask me more about this and the stupidity of the German ministry. But anyway, that's another talk by itself, maybe later on with a glass of wine or whatever. But with a SGRAL, which is about 100 times the collecting area of the Effelsberg telescope, 100 times, we can not only find the rarer system, but we can also time them much more precisely because the timing precision scales with the sensitivity of your telescope. Still, we don't really know how many pulsar black hole systems are there in the galaxies. If you ask a theoretician, it could be 0 to about 10. They ask us to find them first so they can calibrate their models. That's not very helpful. So one thing we want to do, just look at the black hole where we expect pulsars to be. And that's Sagittarius A star, the center of our galaxy. Now, Reinhard Genzel will have probably talked about this studying the central black hole. But if we were to find a pulsar that orbits the central black hole in an orbit of about a few months, similar to what Reinhard wants to find with his infrared S stars, then we can measure the mass in the same way I explained to you before. We can measure the mass of the central black hole to a precision of 1 solar mass. We can measure the spin of the black hole to about 0.1%, and that allows us to measure the cosmic censorship conjecture, which means every black hole has an event horizon. And we can also measure the quadrupole moment of the black hole, which allows us to measure the so-called Noah-Hare theorem. What does it mean? Black holes are simple. When they collapse, they have lost all information from the progenitor star, and they're only described by the mass and the spin and the charge, which you can't measure. And so if you measure the mass and the spin, you can predict what the quadrupole moment should be, and you can compare it, and that gives you a test of the Noah theorem. And that's possible by measuring higher order variations in your residuals. This is here for, you see the amplitude here, these are 2 milliseconds. That's easy to measure with an ordinary garden variety pulsar. So are there pulsars in the galactic center? That's a big question. But fortunately, after 20 years of searching, we managed last year with the Effelsberg telescope to discover one. It's a special pulsar. I won't go into details. It's the highest known dispersion measure, rotation measure. So it's really in the center of the galaxy, 0.1 parsec away, not quite as close as you would like it, but they're rare. This is actually a magnetar. This is a highly magnetized pulsar, of which we only knew 4 about in the galaxy so far. And the fact that we found such a rare object in the center of the galaxy tells us that the more ordinary pulsars are also there. And so that was a nice confirmation. So if you have a pulsar in a galaxy, you do this experiment and compare it with what we want to do with some colleagues, what we call the Event Horizon Telescope. It would be nice to actually take an image of a black hole. It's difficult, but not impossible. What happens is, in the center of the galaxy, you have the supermassive black hole. You have a lot of gas that streams into the galactic center black hole, and it forms an accretion disk with hot thermal radiation, and that radiation is visible in the radio. And in the radio, you would then, if you have a high-resolution picture, you would see the bright shine of the accretion flow and the shadow of the black hole in front of it. And that's what we try to measure. And you can actually calculate, because we know the mass from Reinhardt's measurement, very precise. You can actually measure what the Schwarzschild radius is. You know what the size of the image should be. And you are a little bit frustrated. Because if you look at the galactic center in a radio at low frequencies, this is about 8 gigahertz, it looks like a big blur. It's a strong radio source, but it's blurred because the light is scattered on the way to Earth. The scattering, however, goes down with increasing frequency. And so you have to go all the way up to about 220 gigahertz for the blur to disappear and for the sort of fog to be lifted, and you can see into the black hole. That's what we're trying to do. So what we need is a telescope, radio telescope operating at high frequencies, and there are quite a few on Earth, and we need them all. But in particular, we need the big boys, ALMA, and the new NOEMA, which is going to be put together in IRAM on Plateau de Bure. And then you have a telescope of the size of the Earth. You have the wavelength at high rate, which is very small, and so you have the best possible resolution, and then hopefully we get the image. And why do I talk about it? What does it have to do with pulsars? Well, the image depends on the spin direction of your black hole. But with a pulsar, you can measure this. And so we put in a proposal to the ERC to actually have a combination of the VLBI image and the measurement of the orbit. So from the pulsar, we can determine the spin, because the orbit will be different. That will allow us to predict what the image should look like. We compare it with the image, and then it's hopefully a unique test of theories of gravity to the most extreme you can think of. So that's a project which runs about 6 years, so stay tuned. It just started. So, summary. Again, general relativity has passed all the tests. The alternative theories of gravity, which have failed, and we have strong constraints, but the game is not over yet, because we haven't pushed our test to the limits. I indicated at the end of my talk how we try to do this. It's an ongoing process, but until then, we should be open-minded. Newtonian physics was also valid for 300 years until the measurements became so precise that they pointed out some problems, and Einstein came along and fixed it. So by a combination of pulsars, black hole, and gravitational waves in particular, we hope to gain essential insight. Until then, let me finish with a quote from the person himself. Wie kommt da die pedantische Genauigkeit der Astronomie zur Hilfe, über die ich mich im Stillen früher so lustig gemacht habe? And that's what he wrote in a letter to Arnold Sommerfeld after he realized he can actually explain Mercury perihelion in advance. And if the astronomers wouldn't have measured that so precisely, it would have failed the first test. Anyway, I hope he would have liked this curve. Thank you very much.